All right, Wizards, one of the things we're going to be working on this week is a two-tailed test. A two-tailed test. And so we've seen this problem before. The CEO of a large electric utility claims that 80% of his 1 million customers are very satisfied. Again, this is a statement about the population. To test this claim, they survey 100 customers. That's my sample size N. And they find that 73% are very satisfied. This is a statement about P hat. So based on these findings, can we reject the CEO's hypothesis that 80% of the customers are very satisfied and conclude that the opinions have changed? So since all we're interested in is a change in the opinions, that could be either greater than or less than. We really don't know a direction for our alternate hypothesis. So this is an example of a two-tailed test. So let's start out. Let's establish what our hypotheses are. The null hypothesis states that the population proportion is equal to 0.8. In other words, the opinions have not changed. And our alternate hypothesis says that the population proportion is different from 0.8, which means the opinions have changed. We just don't know what direction they've changed in, but they've changed. The evidence that we've collected against HO, our sample is evidence against the null hypothesis. And this evidence is the following: a sample size of 100, 73 successes in our sample, with a p hat of 0.73. In other words, 73% of that sample are satisfied. So those are the starting details for our hypothesis test. So let's check our conditions quickly. It's set up here, and they were using a simple random sample. So the 100 customers were randomly sampled. Since we're doing a hypothesis test, we need to base everything we do on the population proportion. Remember, the population proportion is assumed to be 0.8. So if the population proportion actually is 0.8, in a sample of 100, which is the sample size that we collected as evidence, I would expect to see 80 customers who are satisfied and 20 who aren't. So both are greater than 10. So our sample is large enough to continue on and use a normal model. This third condition, we'll continue to write this, but this is a condition that's typically not checked a whole lot on the AP exam. But 100 is less than 10% of 1 million customers. So our sample is not too big. And that's what we'd like. We want a big enough sample, in other words, more than 10 successes and more than 10 failures, but we certainly don't want one that is too large. So those are our conditions in context, and our conditions check out. So this is the normal model that I'm going to use. That's the population proportion, or sometimes it's referred to as P0 in the book. That's our null proportion. We're claiming that the population is actually 0.8, or 80% of the customers are satisfied. And this is our standard deviation. And we can refer to that as a standard deviation because we're using what is assumed to be true in our population proportion. We're using that to compute this amount. And so I draw my normal model. This is my P0. Here's my P hat. And it is less than 0.8. But how a two-tailed test works is I want to check in both directions. So I continue on and I try to find this area here like I typically do. But this area is also symmetric to that area over there. And so this is what a two-tailed test is. You're computing the area in both tails. Two tails, both tails. Now, we don't need to write anything on this side unless you wanted to write a z-score. And we'll do more with emphasizing showing z-scores because this is a part of the AP test solution that you'll need to include. So the z-score for my p hat is negative 0.75. The symmetric z-score is 1.75. So I'm looking for areas. What's the chance that I am beyond those two z-scores? So here's my normal CDF down here at the bottom. And when I compute that probability, that turns out to be a 0.04. That is this amount. That's the amount in the lower tail, which means the upper tail is also 0.04, which means my p-value is those two tail areas combined. So my p-value is 0.08, and that is larger than my alpha level. That's larger than my alpha level of 0.05. So this is what a two-tailed test looks like. It's like a one-tailed test, but you're doubling everything at the end. So our conclusions. With a p-value of 0.08 greater than our alpha level of 0.05. This is called the linkage statement. That's called the linkage statement. We'll practice more this week on writing that statement. You're trying to link your p-value to the alpha level. We want to link the p-value to the alpha level. In other words, how does the p-value compare to the alpha level, and what does it mean that we will do? Since our p-value is greater than 0.05, I fail to reject the null hypothesis. So that's my decision, and then we support it. I do not have evidence. I do not have evidence to suggest that customer opinions have changed. So at the very beginning of this problem, we collected evidence in this sample. Our evidence was a sample size of 100 with a p-hat of 0.73. And is that evidence strong enough to reject the null hypothesis? And at the end, we found that that evidence was not strong enough. So that is an example of a two-tailed test. And if you have any questions about this, shoot me a message or ask me in class, and I'll make another video for you. I've got positive feedback from these videos from those who've watched them, so I appreciate that. And again, I hope this has been helpful.